Okay, before we get started into 1.4, I just wanted to show you a few things that are optional for you to do, but might help you to learn and be able to do better on some of the quizzes and exams. So this first one is in 1.3, and it's about matching graphs to their linear equations. And the other one is this, write an equation. So I'll give you an equation and then do the things that it asks here on it. So I'm going to put up the answers to this last one so that after you do it, you can check and see whether you have them correct. So if you want to pause now and try and do it, that's great. All right, but here is the answer key for it. So I'll just kind of put that on there right now. So you can maybe just take a screenshot of it or something, or just pause it and you can come back to it later after you've had a chance to work through it. And then as far as, let's see, where did that other one go? As far as this goes, the practice with linear functions, here's a good function for you to try on here. F of x equals 2/3 x plus 4. And remember, you want to choose x values that are going to make it easy for you to get answers that won't be decimals or fractions there. So a hint to that would be to choose x values that are multiples of 3 on this one, because the denominator is 3. If the denominator was 4, choose multiples of 4. If the denominator is 2, choose multiples of 2, and so on. So probably a good thing to pick on this would be something like oops, why is that not working here? So maybe something like -3 and 3 would be good ones to pick. So anyway, let's get started into stuff from 1.4. And there's going to be a few things that I want to look at a little bit beforehand, just to make sure everything is making sense to you. So first of all, think about this part where, maybe pause the video and quiz yourself on the slope formula and then slope-intercept form of a line. And then do some of these warm-ups to see how you're doing there on these, because sometimes that can give you a little bit of help to just make sure that you're on the right path and knowing what you need to do there. Okay? And if you have any questions, you can always reach out to me. All right. So let's get started here where we're talking about 1.4, where this is applications with linear equations. And so first thing that we need to talk about is how a rate comparing relative change to two related variables is called the average rate of change, or we can call it the rate of change. And this is the same thing as the slope of a linear equation. So when we're talking about an average rate of change or rate of change, we're just talking about the slope when we're dealing with something linear. All right, so let's look at this first problem to practice through. And it's talking about a deep sea diving bell. It's being lowered at a constant rate. After 8 minutes, the bell is at a depth of 600 feet. After 40 minutes, the bell is at a depth of 1,500 feet. What is the average rate of lowering per minute? So first thing to do to set this up, it'd actually be good to write these as ordered pairs. So the information that it's giving us here, we could either write as a table of values, or we could write it as an ordered pair. So either way, whichever way makes better sense to you is what you can do. Whoops. All right, so let's do that. So if I'm looking at that first one, I've got 8 minutes is 600 feet. So 8 minutes, 600 feet. So there's one of the ordered pairs. And then the next sentence gives us the other one. After 40 minutes, it's at 1,500 feet. Okay. And then we can use the slope formula to be able to do this. So remember that the slope formula, maybe I'll just write it up here, is m equals y2 minus y1 over x2 minus x1. So that's what we're going to be using to find this average rate of change. So again, here's our x1, y1, and our x2, y2. And so if I put that in to the formula, we'll have 1,500 minus 600 over, so now we're doing our x's on the bottom, so 40 minus 8. So on the top there, we get 900. Oops. And then on the bottom, we get 32. Let's see if I can get it written in here. And then we just need to divide that out to be able to determine that average rate of change on this. And so if you divide that out, we get m equals 28.125 feet per minute. Okay. So that's what we need to do to find these when it's asking for the average rate of change. So let's look at this next problem. Problem 2 says you have 885 decorative bricks delivered to your house and set down in your driveway. You need to move all the bricks to your backyard. You move a few bricks by hand and quickly decide that it'll take forever, so you go buy a wheelbarrow to haul the rest. You decide to pace yourself by hauling 5 wheelbarrows full of bricks each hour. After 3 hours, you determine that you have moved 245 bricks to the backyard. After 8 hours, you find that you have moved 645 bricks to the backyard. So part A, how many bricks an hour are you moving using the wheelbarrow? So to do this, right, it's saying, okay, we need to find the slope of this. So let's first again make some ordered pairs here. So we know after 3 hours, all right, we have moved 245 bricks. And then after 8 hours, we've moved 645 bricks. Okay, so the x-coordinate on this is our time, and then the y is the number of bricks. All right, so to do this, let's go ahead and use that slope formula again to help us find the answer here to A. So y2 minus y1, so 645 minus 245 divided by 8 minus 2. So we get, I meant 8 minus 3. I don't know why I said 2. 8 minus 3 is our other one. Okay, so then on the top, when we subtract those, we get 400. And then on the bottom, when we subtract those, we get 5. And 400 divided by 5 is 80. So let's think about what we found here, right? 80 what? Well, we're moving 80 bricks per hour using the wheelbarrow. Okay, so that's going to be 80. Then part B, how many bricks had you moved by hand before you started using the wheelbarrow? So this value is the y-intercept of your linear equation. So let's think about this. So remember, we know that we have this formula, y equals mx plus b, where m is the slope and b is the y-intercept, and x and y is any coordinate along that graph. So we can start by figuring this out by putting values in place of y, m, and x, and then we can solve for b. So let's try that on here and see how we do. So we've got, so let's use, I'll just use this second point right here. You could use either of them. But so in place of y, let's put 645. In place of m, we just found that that was 80. X is our value there at 8. And then the b is what we need to solve for now. All right, so let's go ahead and do this. I've got 645 equals, well, 80 times 8 is 640 plus b. So I need to subtract that 640 over. So it looks like I'm going to have 5 bricks. All right, so that was my start amount. That's how many bricks I moved by hand. So I guess after 5, I was like, oh no, I'm not going to do this. All right, so move 5 bricks by hand before starting to use the wheelbarrow. All right, part C. Write a linear function representing this situation. Use t as the number of hours you work and q of t as the quantity of bricks moved after t hours. Okay, so we're going to start off with q of t. All right, that's the number of bricks we're going to be moving. So it's kind of like we're going to set it up with this y equals mx plus b, but using the things that they want us to here. So we know that 80 is our slope, so I'm going to put that in here. And then t is our time. And so how many hours it's going to take. And then 5, so we'll put plus 5 because that is how many bricks we started off with. So that's our start amount. All right, find the value of t where q of t is 885. So remember, we had 885 bricks that were delivered. And so we want to make sure that we can figure out how much time it's going to take to move those 885 bricks. Okay, and then notice also it says write the answer as an ordered pair. So let's go ahead and put this in here. So I've got, in place of my q of t, I'm going to put 885 equals 80t plus 5. And then I need to solve this for t. Okay, so let's start by subtracting that 5 over. So I get 880 equals 80t, and then divide both sides by 80. And I get t equals 11. All right, so let's see. So it says to write it as an ordered pair, so let's do that. So our t, remember our time is what's first, and then our q of t is the number of bricks, so that's what's second. So 11, comma, 885 is our ordered pair there. All right, and then on part E, we already found that here. So after using the wheelbarrow for 11 hours, I will have moved all of the bricks to the backyard. Okay. All right. So think back to the very first section in the book where we were talking about this, you know, how there's like climate change that's going on. We were talking about the carbon dioxide in the atmosphere as well as the carbon dioxide in the water and how that carbon dioxide in the water is making our oceans more acidic. And so that's kind of what we learned about this graph in there. Well, with this, we're able to actually do a lot. So if you click on that, this link here, it's going to take you to an interactive graph, and that's going to help us be able to fill out this table here below. So let me see, let me pull that up, see if we can look at part of this. While we're doing this, let's see here, make that a bit smaller so we can see. Okay, so this is a nice interactive graph here that you can click on and be able to see to be able to fill in some of the stuff here. So you can see that the first thing is filled out for us here. So January 2005, the CO2 levels were 378.63. And so then we could write that as an ordered pair there. So now we want to figure out the CO2 levels from the graph at all of these different times. So let's start off at January 2008. So it kind of moves pretty quick here, but let's see here if I can, whoops, sometimes hard to click right in on it. All right, so we can see here. No, it won't let me click it. It was before. All right, well, I'm going to fill this in for what I was doing, and I'll let you kind of play around with what you have here. So probably it'd be a good idea to maybe pause it and see if you can get that table filled in, and then I will also help you get that filled in as well. Okay. So fill these in. So 385.78 and then 391.5, 398. Let me see here. In better. So 398.04. Looks better. Let's do 406.04. 413.59, and then 419.18. Those will be a little bit easier to see there. All right, but make sure you look at the graph and understand how to do that. And then we're going to be answering some questions with this by filling that out. So, find the average rate of change using the table above, and the change in the atmospheric CO2 from January 2005 to January 2014. All right, so the ones that we're looking at, all right, we're going to look at this one and then this one. That's where we want. So again, remember, we're kind of using that same, the rate of change is slope. So we're using the slope formula. So we're going to start off with this. It's going to be our y2 and our y1. So let's subtract those. So I've got 398.04 minus, that one in 2005 is 378.63. And then our years are 2014 minus 2005. All right, so if we subtract those on the top, just use your calculator to help you do that. get 19.41. And then on the bottom, when we subtract those, we get 9. And so this means when we divide that, we find that the increase in CO2 per year is about 2.16 parts per million. All right, per year. So that is what it's been raising, at least between those two, or between those years that we have on that. Okay, so let's keep going. So when we're talking about the initial value, we also call it the start amount, and that is talking about the y-intercept when we're dealing with story problems. So keeping that in mind, let's think about what we are having here. So what is the start amount of the atmospheric CO2 in 2005? So we're saying if there wasn't any data before January 2005, then this is where we're starting at. So our start amount would be those CO2 levels there. All right, so our start amount would be 378.63 parts per million. And then wants us to write a linear model representing the increase of atmospheric pressure from January 2005 to January 2014. So remember, we're going to be using, again, that y equals mx plus b to be able to set this up. So on this, we got y, which is going to be, the, let's see. So y is the levels of CO2 during a given year, right? So x is going to be the years, and y is going to be the total amount of CO2. So we've got y equals, well, we found that slope to be the 2.16. So let's put that here. So 2.16. And then times x, depending on how, which year it's in. And then plus our y-intercept is 378.63. Okay, so remember here, this x value is the years, and this y value, it represents the amount of CO2 in that year. Just to be able to understand this a little bit better. All right, so let's use that information to deal with this last part. Use the model that you wrote above to predict the amount of atmospheric CO2 in January 2040. All right, so remember, X is the number of years since 2005, because we were saying 2005 is kind of like our starting point on this. So we need to figure out how many years it's going to have been to be able to plug that in for X. So if we do 2040, right, minus 2005, which is the starting year that we have, then that means this is going to be in 35 years, right? 35 years later, how much CO2 will there be? All right, so let's plug those things in. So y equals 2.16 times 35, that goes in place of our x, and then plus 378.63. All right, then put that into your calculator, and when you do that, see, it comes up to be 454.23 parts per million. And that's going to be in the year 2040. And scientists have said that anything above 400 parts per million is going to cause a lot of problems for us. So, climate change we already see happening, but this is going to make it even worse. And when it gets to 500,000 parts per million, it could be really bad. So So there's definitely been some things that governments have been trying to do around the world to help us, keep this amount of CO2 in the atmosphere down. And so just something we got to keep working on. We can't get rid of it altogether, but we can do our part to decrease how much it is rising. All right, and then so let's got just a couple more things here to look at. So on this one, Marcus currently has 150 songs in his music collection. Every month he buys 20 new songs. What is the initial value in the scenario, right? Remember, that's going to be the y-intercept. So initially he already has 150 songs. So that's our initial value. The average rate of change is he's going to buy 20 new songs each month, right? So 20 per month. So that is our average rate of change. So the formula for this, so number of songs equals a function of time. So we're going to use t in it, but our rate of change is 20. So 20 times t, right? And that t is dealing with months, right? How many months? And then plus 150, because he's already starting off with 150 songs in his collection. So part D, how many songs will he own in a year? Well, remember, T is in months, so we need to put year as months. So remember, we're going to be using 12 months for this, not 1 for our T. So let's put that in there. So N equals 20 times 12 plus 150. So 20 times 12 is 240 plus 150. Add those together, we get 390 songs, right, in 1 year. That's how many he's going to have in his collection. All right, and then part E, how many months will it take to grow his collection to 650 songs? Well, that's the number of songs, so that's going to go in place of our N this time. So 650 equals 20 times T plus 150, and then we need to solve that for T. So let's start by subtracting that 150 over. 650 minus 150 gives me 500. So 500 equals 20 times T. Let's divide both sides by 20. 500 divided by 20 gives me 25. But 25 what, right? We need a label on it. Remember, any word questions need a word answer. So T represents the number of months, so it's going to take 25 months to have 650 songs in his collection. Okay. Oops. What happened here? All right. All right, and so then these would be good to make sure that you know how to get set up on your own. I think it would be good to maybe, pause it and try and see if you can get these set up on your own, and then unpause it, and then you'll be able to, see what we did here, okay? Okay, so here is the answers to this, so you can kind of work through it on here. So remember, when you are trying to write these equations, you need to know the slope and the y-intercept. So looking at this, right, the weekly pay for a salesperson at Excellent Electronics starts at $200 plus 5% of their weekly sales. Use X to represent the value of the salesperson weekly sales in dollars. Write a linear equation to represent their weekly pay. So we need to go through and figure out some of these things. So slope is the average rate of change. And think about how, like when we're talking about slope or any kind of percent, right? It's a rate. And so that kind of helps you to know that that part's going to be your slope. I mean, think about it when you have like a loan or something, you got an interest rate is what they call it, but it's a percent. So that kind of can help you. But 5 is not what we're going to use. It's 5%. So we need to change that to a decimal of 0.05. And then our y-intercept is the start amount, which is $200. So, so the pay there, you're going to get $200 no matter what, and then more depending on how much you sell. So if we plug those into the slope and the y-intercept, we have y equals 0.05x plus 200. And then the next part says, what will their weekly pay be if they sell $2,300? So that sell, remember, is going to be what we have in place of x here. X is the value of the salesperson's weekly sales. All right, so that's how much they sold. We'll put that in place of x. When we solve that through, we get $315 if they sell $2,300 that week. Okay, hopefully you've tried getting this, all set up and everything. So on this next one, we're talking about shipping a package to Juneau. So there is a fee, right, that just a flat fee that you have to pay of $13.50, but then they charge you more for how much it costs, so 75 cents per ounce. So we're going to write a linear equation again here. So C is the cost of shipping, W is the ounces there. And looks like I didn't use W and C there, but I think you get the idea here. So make sure you know the slope, right? And again, the reason why we can tell this is a rate, because it's like per ounce, right? Or per month, or, something like that is going to be your rate. And then the y-intercept is that flat fee, right? So set that up, put those numbers in to get that formula for this. And then the last question, how much will it cost to ship 24 ounces? So this is talking about the weight. So that's where we're going to put the 24 in place of. And solving it through, we can see that it's going to be $31.50 to ship that. All right. And then this last one here is talking about a plumber and a service call here. So a plumber charges $25 for a service call plus $50 per hour of service. All right, and again, we can see here $50 per hour. That's helping us know that that's the rate, and you're going to charge a $25 flat fee. So that is going to be our y-intercept. So setting that up, we can see that we're going to have y equals 50x plus 25. All right, 25 is our start amount. 50 is how much they're charging per hour. And then it asks us to determine the cost if it works for 8 hours and for 10 hours. So for 8 hours, we plug that in. You can see it's going to cost $425. And at 10 hours, when we plug 10 in place of x there, we find that he's going to charge $525 for those 10 hours of work. All right, I hope you found this helpful in being able to solve and set up these applications involving rate of change and also the start amount or the initial value.